nuclei that are meta-directors and deactivating groups are ones that have an electron withdrawing group connected to the ring, but not with a lone pair of electrons on the atom directly connected. I said that in a really clunky way, so try it again. Notice we have this ester here connected onto the benzene ring. This carbonyl carbon here, as we've seen like 1,000 times now, right, is that there's a dipole here in this carbonyl bond, so that the carbon is electrophilic. It's pulling electron density away from the ring. So that means overall this group is withdrawing electron density, deactivating the ring, making it less nucleophilic, and making it unfavorable to have the carbocation situated on this carbon here because it's next to this electron withdrawing. But you'll also notice there's no lone pair of electrons on this adjacent carbon, this carbonyl carbon here. So you do not have this resonance stabilization. In other words, the substituent cannot dump electron density into the ring to stabilize the carbocation. So this is why it's a meta-director. If you have the carbocation here, it's just bad news energetically because this substituent is pulling electron density away. And so when we look at a couple more of these substituents, we'll see that that's the general trend. But there's one key exception. I'm going to make the pencil a little thicker here. Let's try this. It's maybe too thick. We'll use the middle one here. Should have practiced. Okay, there's one key exception to this idea, and these are the halogens. And this is one of those cases. So, great, it makes sense. We'll change that here in a little bit, I think. And so the halogens are an exception, meaning that, let's just assert what ends up happening, is that they are actually deactivators, or deactivating, but they're orthopara-directors. It's supposed to say orthopara-directors. So before we've seen that activating groups are orthopara-directors, deactivating groups are meta-directors, except the common one is that the halogens do not follow that trend. They're deactivating, but they're orthopara-directors. So if we were to take something like, probably won't draw out all of the resonance structures, this chlorobenzene, and let's just stick with nitration, we would see that the reaction actually happens much slower than with benzene alone, and we'd end up having ortho, meta, para substituents. However, now this would be a major product, this would be a minor, and then this one will still be a major. And who knows, maybe this one is more the major product, but we're not going to split the difference between ortho and para. Now the question is, we need to come up with why is it deactivating? Why is it an orthopara-director? So first, addressing the deactivating part is that these halogens are quite electronegative compared to carbon. So there's a dipole, there's a significant dipole pulling electron density towards the chlorine, which is going to reduce the nucleophilicity of the aromatic ring. So we can think about then, so activating is due to the dipole. All right? Now, why is it actually an orthopara-director? Let's put a line in between. So why orthopara? Let's do the same analysis that we did last time. Just to refresh, the strong electrophile is that nitronium ion. We'll collapse this down. Probably should have written this a little bit to the left. We'll make it bigger here. I don't know if they're all going to fit. So we're going to end up having, let's just put the nitro group in our standard spot here. Now we have this rhenium ion, our important intermediate, and we can draw resonance structures. And since the whole point here is to talk about the chloro, let's include that. So now let's draw our resonance structures. Still have the nitro there, chloro. So we're doing exactly what we did actually with the hydroxyl group. Okay, I think I messed up something here. Oh, my eraser is big. That's a problem too. Okay, looks like a. Let me go backwards. There we go. And now we have our different resonance structures of our carbocation. So positive charge in this carbon, on the left carbon, and on the top center carbon. And now the key thing is, it would make sense that having this positive charge adjacent to this electron withdrawing chloro group should be highly unfavorable. And it would be. However, the key thing is this chlorine has all of these lone pairs of electrons on it. So it can actually donate electron density to form another resonance structure. This is the most important one, so we're just squeezing it in here. So what this is going to do is to generate one more resonance structure. And what you'll notice now is this chlorine in this resonance structure is giving up a lone pair of electrons. So it still has two lone pairs. Let's make those red to be consistent with the previous one. And now it has a positive formal charge. Oops. And just like with oxygen and nitrogen, this one, now, by this one I mean this resonance structure, every atom has an octet of electrons. So this is actually the major contributor. I know it might seem a little bit strange seeing a positive charge on an electronegative atom like chlorine, but this can actually happen. And so, of course, this is an overall combination of all of these resonance structures, the resonance hybrid. But the key thing here is that the chlorosubstituent can stabilize the carbocation intermediate through resonance, in which you can actually generate a resonance structure in which every atom has a full octet of electrons. So we're going to assert, now we won't draw everything out because we did it with the other one, so that's okay. If the nitro group is added at the para position, it's the same thing. You can draw the same series of resonance structures. However, if the nitro group, or whatever the electrophile might be, is added at the meta position, then the chloro group cannot directly participate in resonance stabilization. So overall then, in terms of activating, deactivating the halogens, and we use chloro as an example here, slows the reaction down because it is pulling electron density through induction, pulling electron density out of the ring. So that's why it's a deactivating group. However, it's an ortho pair director because it can be involved in resonance stabilization when the group is added at the ortho or para position. Okay, so that's the important exception to this. So Crystal asked if it's meta, what cannot be done again? Well, okay, let's draw it here, actually for the comparison. So let's take the same thing, and this time I'll actually put it over here. So here's our chlorobenzene, or at least parts of it. And now we're going to put the nitro group at the meta position. So chloro here, nitro here, start with our carbocation up here. Now if we draw our resonance structures, what you'll notice in the different resonance structures, it's like the positive charge kind of skips over the atom with the chlorine. So we have this resonance structure, and one more. We move these electrons up here. There's our nitro group. So now we have those are the double bonds, and there's our positive charge. So excellent. Yeah, happy to explain. And so now here, for the meta, so this one here, we'll use the purple again. This is with ortho para. This is with meta addition. And if the nitro group is added at the meta position, you have resonance structures that you can draw. So we can have resonance stabilization of this intermediate, these three different resonance structures. However, what you'll see is that in none of these resonance structures is the carbocation on the atom that's directly connected to the chlorine. So it's either to the right or to the left or to the bottom here. But you cannot draw a resonance structure that has the positive charge on this atom that's connected to the chlorine. So what that does is it prevents the chloral group from contributing to the resonance stabilization through its own resonance contributions. In other words, you cannot form a resonance structure where every atom has an octet of electrons. And energetically, that's quite favorable. So you can't do that with the meta addition. So that's going to be that'll make this intermediate higher in energy, so less favorable to form. So, but you can do that with ortho-para substitution. So those will be the major products. So it all comes down to the resonance stabilization.